thanks for the invitation to come today. Jeremy, as I think you mentioned, I was at Boston University in the College of Engineering, and 8 years ago I moved my lab. I had the opportunity to move my lab to Boston Children's Hospital. And the main motivation there was putting myself in an environment where I'd be exposed to the clinical problems, because I think it's a general issue that as an academic, somewhat isolated from the clinicians, you can suppose what their needs are, but you really can't dive in and understand what those needs are unless you're intermingling with them. So that was my goal in moving to the hospital. And so I've got a number of different projects going on, but I'm going to talk to you about our work in interventional cardiology today as an example of a need, and then some solutions we've been working on. And ironically, this is not really pediatric, but it's a wonderful example. So if you go to interventional cardiology conferences, what you'll see is that there's a marvelous variety of sophisticated devices that have been developed as alternatives to surgical repairs of heart valves. Okay, so I've shown a few here. The ones on the left, the MitraClip and the transcatheter valves, those are probably perceived as the two home runs of interventional cardiology right now. The MitraClip is for repairing mitral valve prolapse, and what you see here is you've got this crazy looking device delivered by catheter between the two leaflets of the mitral valve. It creates a double orifice valve and thus prevents, hopefully, regurgitation without any open surgery. Secondly, transcatheter valves that you've probably heard more about, rather than go again through open heart surgery, aortic valves are delivered on a daily basis. Mitral transcatheter valves are being developed. On the right side, I've shown you a couple other repairs for mitral valves to replace chordae. So it's marvelous what devices are being developed, but the focus has been entirely on devices as opposed to the imaging used to deliver the devices, which is ultrasound and fluoroscopy, or the delivery systems, the catheters themselves. And so as far as motivation in terms of saying, well, is this a problem? I give this as sort of an example in jest. I went to the Transcatheter Cardiovascular Therapeutics Conference, TCT conference, back in 2012, and there was a clinician who, well, let me just bounce back just to remember this MitraClip, okay? It's a clip between the two leaflets of the mitral valve. So at TCT, there was a clinician who said, look, I can not only deliver one MitraClip, I can put two MitraClips on that valve, and there you go. And there's the fluoroscopic image, which of course shows the two clips, but doesn't show the tissue because it's just x-rays. And then as you go on, there was another clinician who says, well, I can put three clips. And you know, look what I can do. But you notice all three clips are not pointing in the same direction, which is a little bit scary, right? And then the following years, you know, then they started, well, I can do 4 clips. And then I can do 6 clips. And you start wondering, in the titles of their talk were things like, I can't grasp the leaflet, or pushing the anatomic limits. And you've got to wonder, you know, what are they doing? Can you really put 6 clips on a leaflet? And maybe you can, but maybe they need that many clips because they really can't see well what they're doing. Or if they could see well what they were doing, maybe if they had a little more dexterity and they weren't trying to grab 2 moving leaflets at the same time, they could get by with fewer clips. So that's sort of our motivation there. Today, I'm going to look at a simpler example. This is part of an NIH-sponsored grant where we're looking at how we can improve imaging and dexterity for transcatheter procedures and understanding, you know, which of those are important. What's the minimum improvement in technology you need to solve the problem? So this particular example, which is paravalvular leaks, is something which occurred with the first few generations of transcatheter valves. So there are a few bloody pictures in here. My apologies for that. At least we've all leaked. So with paravalvular leaks, the idea is you put in this new valve, which doesn't leak inside, but because you've got a bad connection with the surrounding tissue, you get leaks on the outside of the valve, which could be just as bad as the leaks that you had originally in your valve. And so if you've avoided putting this person on cardiopulmonary bypass to put a transcatheter valve in, the last thing you want to do is give them surgery, open them up to try to fix these leaks. So the approach that's been developed is to go in with a catheter and basically thread a guide wire through that leak using ultrasound and fluoroscopy, guides, the kind of images you see on the right, and delivering a repurposed vascular occluder, as you see here, sort of a nitinol mesh that pops open to fill that hole, which will then epithelialize and stop the leak. So we undertook this particular application with the understanding that it was much more likely this was an imaging limited problem rather than a dexterity limited problem, but we wanted to explore both. So this gives you sort of the big picture of, do we need robotics to provide dexterity, or if we just have improved imaging at the tip of the catheter, would that solve the problem? And so I'll give you a little explanation of what we have going on both approaches. So in terms of robotic dexterity, we're using a technology that my lab developed a few years back, which we call concentric tube robots. Hey, I'm not a marketing guy. I didn't come up with a fancy term. Concentric tube robots, the idea is we take super elastic tubes and we pre-curve them, insert them one inside the other. So this is 3 tubes which we insert one inside the other to come up with this continuous curve. And then we have a motorized drive system which would be, outside the patient. As you rotate and translate the tubes at the base by this drive system, you get this overall coordinated motion on the right. And so you can turn this into a robot, as shown here, being teleoperated, and it gives you sort of the scale. It's like a 3-dimensionally curved needle. On the right, that happens to be a scaled-down version of the puzzle canoodle, which was a favorite of my kids a number of years back. The forceps there are 1 millimeter wide forceps to give you an idea of the scale, and they're being teleoperated. So we have the 6 degree of freedom joystick, whatever direction you point the tip of the pen in, the tip of the robot points in the same direction, and as you translate, the robot arm translates through. I can't show you what it's doing inside the blood-filled heart, so you've got to look at the puzzle to just get a sense of how it operates. So that's the dexterity part. We also want to compare the value of imaging. So what we've been using is endoscopy inside the blood-filled heart. And so the concept here is that you take a standard endoscope system, we make our own, but think of putting a diver's mask over the lens at the tip, and when you press that up against the tissue, the blood is displaced, and you can see right touching in front of you. Okay? So our first version, we had this tissue removal tool, and we're going right through the wall of the heart, and it's sort of in woodworking terms, it's sort of a router to control the removal of tissue. I don't think you can see anything in this image, I'm sorry, but the point was you could see the endocardium being removed as you removed it. We scaled that down to deploy these occluder devices. In these that we make in the lab, we use a camera that's 1 millimeter on an edge with an LED for illumination, all enclosed in a soft silicone tip with a working channel. We have this in terms of a hand tool to consider just the impact of better imaging versus on a robotic catheter. And of course, in our first animal procedure, well, I'll tell you about those in a minute. So first of all, if we want to test this, you can try to test this stuff on the bench top in some sort of, pulsatile model. That's nothing like testing it in a real animal. So we needed to do animal studies. So what do we have to do? We have to create a leaking aortic valve in a pig. That's what we use as the closest model to human. You can't buy pigs with leaking aortic valves. We went to all the valve companies and said, would you donate your valves to us? And they said, well, write a proposal. We wrote a proposal. And then they would call me back a few months later and say, Pierre, so you want us to give you our valve, you're going to make them leak, you're going to repair them, and then you're going to publish this. And I said, yeah. And he said, why would we want to do that? So we had to go back and basically make our own valve. So I had this French postdoc, Benoit Rosa, and he jumped on this with one of our surgical fellows. We 3D print a titanium frame, sew fabric on it, put a sewing ring, and what you can see is we've included 3 places for paravalvular leaks that are maintained in our gaps in the sewing ring. And as Benoit got on with this project, he got very fast at doing it. So he had beforehand, typical guy, he'd never sewn anything in his life. At the end, people were bringing him clothing and asking him to repair their clothing. And he would look up and say, silver pro-week. So it was a fantastic effort, but we took these things and we had to go into the surgical animal surgery lab. The beauty of being in a hospital is I roll my robot onto the elevator, you take the elevator down to the basement, there's our animal surgery rooms. We have great support from the clinicians. One of the clinical cardiac surgeons comes over, put the pig on bypass, install the valve, restart the heart, look, confirm that we have leaks with echo, and then go in to plug them. So first time around, we just used endoscopy on the end of a stick. This, if you watch this video, this is the view inside the beating heart of the pig. We found the leak, the red spot outside the valve, the center of the valve is over here. You can see us deploying the device into the leak. You'll see it popping out. There's a little screw connector here, which you can see is released. And in just a second here, you can see it coming out, being released, and bang, there's the release connector. And so you didn't get the full glory of it, but that's inside the beating heart. You get this beautiful view of what's right at the tip. And the thing is, using this imaging, we were able to do this. Now, it's transapical, which is certainly transfemoral, but we could do this in 3 minutes on average, close one of these leaks, okay? So you ask, okay, if you give them, and I have to have the other result here. So the typical, if you look at the literature, what was the state of the art? They were using some very cool multimodal imaging, preoperative imaging combined with intraoperative echo and fluoroscopy. It was taking them 20 to 30 minutes of fluoro time, foot on the pedal, not procedure time, just exposure time to close one of these things. So clearly, imaging technology was the solution here. But I'm a medical robotics guy. It's like, son of a gun, what am I going to do with the robot? There's no way the robot is going to be faster in 3 minutes. So we started thinking about it. But let me just show you. Of course, we had to try it anyway. So here's the robot doing the same thing. These views are synchronized. So this is the view around the valve. This is the view that you're seeing in the excise valve. He's going to come over and see a leak right here. So here's the inside of the valve. There's the leak outside there. Here's the working channel that we can center right over the leak to deploy a device. So the robot works. It's really cool, but it ain't going to make this any better. So what do we do? Yeah. Well, what we've done is start thinking about how are robots used successfully in other industries besides medicine. I toured the Amazon robotics factory where they have these robots that move the shelves over to the guy that's packing the box. These things are so cool. They, after they're manufactured, they're being tested, they actually drive up onto the shipping pallet to be shipped out, right? The point is there's nobody operating individual robots. There's a group that's being supervised by someone. And so what if we could bring elements of that to medicine? And so there was an editorial that a few of us contributed to in Science Robotics back in March, looking at the different levels of robot autonomy. And that's what we're working on right now. We're working on having the robot navigate from the apex of the heart, find the aortic valve, navigate by itself around the aortic valve to find where it thinks the leak is, and then saying to the clinician, would you please confirm, do you think the leak's here, should we deploy a device? So that's a bit of where we're at and what we've done on one problem. I thank you very much for listening.